All right, hello everybody. Today we are here for our next video on our Unit 2 polynomial and rational functions. And today we're going to talk about holes. Specifically, graphing holes that happen when you have rational functions. All right, so you probably learned about these in Algebra 2, but if not, we're going to go over them today in class-ish / video, whatever you call this. It could be class, whatever. It would be class if we were in person. All right, let's do this. So here we go. All right, so first things first, rational functions can have holes in their graph. This happens specifically when a factor is simplified out of both the numerator and the denominator. All right, now, generally we would say that anytime a number can be put into the denominator of our rational function that would make it a 0 on the bottom, it would create a vertical asymptote. But if something can be simplified out before it's getting to the graphing point, then it's not going to make an asymptote anymore. It's going to create a hole. So graphically, this is not going to be an asymptote. This is going to be a circle in your graph, a point on your graph that it kind of jumps over. So you get really close to it, and then you're kind of graphing, and then it jumps over that one point, and then it keeps going. So it's not an asymptote. It's just like a skip in your graph. All right, so when you graph a hole, it's not an asymptote. It's more like a skip in your graph. All right, so it's also, so I said it's not an asymptote, it's like a skip in your graph. So asymptotes are lines, right? Either vertical or horizontal, or next video you'll learn about slant asymptotes. Anyways, so it's not one of those. It's not a line, it's a point. Okay, so not a line, it's a point. All right, and when you graph it, you're just going to do like an open circle. So instead of a dot that you fill in, it's an open circle. And when you graph it, you just kind of go to that hole. You kind of like don't go through it. You kind of like go up to it, and then right after the hole's over, you just continue on your graph. All right. Now, finding the coordinates for a hole. So the x value that you're going to get to find your hole comes from what you simplified out of your equation. All right. So the x value comes from the factor you simplified out of your equation. Okay, so generally you're going to have like a factor on the top, factor on the bottom, they get to simplify out. All right, so that's going to create a hole. All right, and the x value for your hole comes from whatever x value would have made that factor equal 0. So say, for instance, you had an x minus 1 on the top and an x minus 1 on the bottom. They can simplify each other out. So your hole's x value is whatever x would have made that equal 0. So if it's x minus 1, then positive 1 is your x value of your hole. All right, your y value comes from plugging that x into the simplified equation. Okay, so once you simplify out that factor, you can find your x value for your hole. Then to find the y value, you take that x value, you put it back into the equation, the simplified equation, all right? And then whatever y value you get, that's the y value for your hole. Okay, so that's really all for notes for today. Now we're just going to go through an example problem of when you would see a hole in your graph and what they look like. Okay, so here's our problem. It just says find all the information about the rational function listed and then graph the rational function. All right, so unlike the one that we did together on the previous video, we're actually going to start by simplifying our equation because we want to find any holes first. It's going to make our problem easier to handle, and it's 11:30 p.m. right now. So, getting a little tired. This might be my last video for tonight. I want to do one more, but I don't think I'm going to make it. It would be a really bad video, I feel like. We'll see. Okay. Anyways, so when we can simplify out first, it's going to make doing everything else much easier. So, start by factoring and simplifying. All right, so we have 4x minus 8 in our numerator. I can factor out a 4. That leaves me with x minus 2 over, all right, and in my denominator, I have x squared minus 5x plus 6, so I'm looking for two numbers that multiply to 6 and add to negative 5. All right, so it has to multiply to a positive number, but it adds to a negative number, so they must both be negative. All right, 3 and 2. So x minus 3, x minus 2. Okay, so this is a good start because I see that there is something that I can simplify out of both my numerator and my denominator. I have an x minus 2 on top of both. Okay, so this tells me that I have a whole. All right, now the x value for my whole comes from whatever number would have made this factor equal 0. So my x value, all I have to do is take x minus 2 and equal it to 0 and solve for x. So that's going to give me x equals 2. So I have a 2 for my x value of my whole. Now I'm going to rewrite it simplified. So that's 4 over x minus 3. That's all I have to deal with now for the rest of the problem. I don't have to go back to the original for anything. All right, so now I need to find the y value for my whole, and I'm going to get that by taking my x value and plugging it into that simplified equation. So for the y value, I'm just going to do 4 over 2 minus 3. All right, because my x value that I got was 2. So I'm just plugging the 2 in for x, and now I'm going to simplify. So 4 over 2 minus 3, that equals 4 over negative 1, which is negative 4. So the y value for my whole is negative 4. Cool. I can go ahead and graph that if I want to. So I'm going to graph a whole at 2, negative 4. So 2, and then 1, 2, 3, 4. And I just graph an open circle like that. That's a whole. That's what it looks like in my graph. It's just an open circle. Okay, so next I can do my x-intercept and my y-intercept. So x-intercept, I'm going to set y equal to 0 and solve for x. So it's 0 equals 4 over x minus 3. All right, well, if I multiply both sides by my denominator, it's just going to become 0. So I end up with 0 equals 4. This is never true. So I don't have an x-intercept. So it doesn't cross the x-axis, which that's fine. All right, y-intercept. All right, this is when I plug a 0 in for x and solve for y. So I have y equals 4 over 0 minus 3. So that is negative 4/3. So my y-intercept is 0, negative 4/3. All right, so I can go ahead and graph that. So 0 and then negative 4/3 is a little past negative 1, right? So somewhere around right in here. There we go. There's my y-intercept. Moving right along. Vertical asymptotes, I'm going to set my denominator equal to 0 and solve for x. So I have x minus 3 equals 0, so x equals 3. So my vertical asymptote is x equals 3. I can go ahead and graph that. So 1, 2, 3, boop, 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 do, 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 do. X equals 3. Perfect. Moving right along, horizontal asymptote. All right, I'm going to do Bobo Bot needs DC, and you can do it to the original if you would like to, or you can do it to the simplified version. It's going to be the same answer either way. Sometimes it's easier to go back to the original, especially if you have factors. It might be hard to, like, especially if we have like coefficients to figure out what the number, like if exponents are the same, divide coefficients. Sometimes it's hard if it's in factored form to figure that part out. So I might just recommend going to the original for the horizontal asymptote, but it doesn't actually make a difference. Sometimes it's just harder to see when you go to simplified form. But anyways, this one has the biggest exponent on the bottom. So this is a Bobo. All right, which tells me my horizontal asymptote is y equals 0, which is why we didn't have an x-intercept. All right, so here we go, y equals 0 equals 0. All right, now you can go to your calculator to graph this one, but this is kind of an easy rational function to graph. So I'm just gonna go ahead and sketch this. It only has one vertical asymptote. Those ones are usually the easier ones to handle. And then I know it's just gonna be mirror image over on this side. Sometimes though, when you have multiple vertical asymptotes, that's where it gets kind of weird because you never really know what's happening in between. Sometimes it's gonna be like a little cubic function. Sometimes it looks more like a parabola. So it just kind of depends on the problem. So, but generally if you just have one vertical asymptote, it's pretty standard rational function shape. So usually those ones are pretty easy to graph. Okay, last but not least is my end behavior, my limits. So I have the limit as x goes to infinity. So I look as x gets really big and goes towards positive infinity, it looks like my graph is approaching my horizontal asymptote, which is y equals 0. So it's 0. All right, as x goes to negative infinity, so going backwards, it also is approaching my horizontal asymptote. So the limit is 0. All right, now as x approaches my vertical asymptote from the positive direction. All right, so as we come, so our vertical asymptote, as we approach it from the positive direction, I see that my graph approaches and then turns up. So I would say that my limit as x goes to the vertical asymptote from the positive numbers is positive infinity. All right, and then on the other side over there, as x approaches from the negative direction, I notice that my graph is going to go down. So I would say that the limit as x goes to the vertical asymptote from the negative direction is negative infinity. That is it for that problem. That was a pretty short video. I hope that helped you guys get a little refresher on holes with rational functions. All right, until next time, bye guys.